Okay. Yeah, so I'm going to talk about internotide beam generation by an abyssal hill in the middle of the Mid-Atlantic Ridge, and that is part of a work I did with Bruno Ferron at LOPS, and we took part to the MOMAR cruise in June 2022, last June, and yeah, so I'm going to present some of the results we had. So a little bit of context. This is an artistic view of the Mid-Atlantic Ridge with the mountain, with the submarine chain of mountains, and there are a lot of hydrothermal vents all along the ridge. And one of them, one of the most iconic one, is called Lucky Strike, that is south of the Azores, and you can see that there are some very typical ecosystems with shrimps and crabs and different species that are typical of these events, and that deserve attention for the biologists. And this site is part of the EMSO Azores, with European Multidisciplinary Seafloor Observatory site. And as part of that, there are some repeat missions every year to monitor the ecosystems and the geochemistry. And sometimes they allow some physical oceanographers on board, and that's why we went to the cruise with Bruno. And during the daytime, there's the deployment of this big submarine here that was used for servicing the moored stations for seismicity and biogeochemistry. And during nighttime, we had time for doing some physics, and we deployed a VMP for measuring the dissipation of turbulent kinetic energy. And we also made some SADCP transect to get some continuous measurements of horizontal currents. And this presentation is about the currents that we measured. So the data we used are shipboard, or sometimes called surface or vessel-mounted acoustic Doppler current profiler data. The schematic here is from Teledyne. So there are some continuous measurements of horizontal currents with a 38 kilohertz ADCP, and the currents were being averaged with a sampling of 120 seconds. The vertical resolution of the currents were around 24 meters, and the beam centers were between 50 meters below the sea surface to like roughly 1,500 meters. Sometimes a little bit, we could go a little bit deeper than that, but it really depends on the quality of the echo. And the questions that are of interest to us around this site is linked to what we've been doing with some high-resolution modeling studies. So it's been a few years now that we are running some simulations with the Croco model. You're seeing on the figure here the relative vorticity that's generated by a sub-mesoscale and tide resolving simulation with a horizontal resolution of 750 meters. And you can see a lot of different small-scale structures all around the ridge. The yellow star is showing the Lucky Strike site, but we have we struggle to assess the realism of the simulation because we lack some observations. And among the questions that are of interest here is the variability in space of time of the velocity profiles, the persistence of some vertical modes, or is there some geographical variability? And what's the variability of the internotide field in general in space and time, and what's their interaction with the background mesoscale field and sub-mesoscale field? As you can see, the smaller studies that are resolved in the simulations have diameters of something like 30 kilometers. So we decided to repeat a section that crosses an abyssal hill that was really close to the Lucky Strike site. So there were a lot of constraints of what we were able to do in terms of ship time. But there's this abyssal hill. So you're seeing on the figure here, the white dotted line is showing the main axis of the hill. And it's a good candidate for generating waves because it's quite steep. Its dimension is around 1,000 meter high over 5 kilometers, so the slope is very steep. It's actually supercritical with reference to the semi-diurnal internal tide. And the axis is almost perpendicular to the ship track. So we expected some strong internal waves to be generated over there. And to get more into the details, so the section is roughly 40 kilometers. And we chose to repeat 7 times this east-west section that could be completed during the night. And so it took us around 6 hours to complete the section back and forth. It crosses the abyssal hill, as I said, and the barotropic tidal currents reversed while the section is being completed. So that's a bit of a challenge then to decipher the observations between barotropic and baroclinic signal. But the amplitude of the barotropic tidal currents was between 4 and 5 centimeters per second, as you're seeing on the right-hand side figure here. That's the prediction of the tidal currents using TPXO. And yeah, that's it for the context and method. We also had some 17 CTD casts all around the Lucky Strike site that allowed us to compute the mean stratification, and from then we assessed the vertical structure of the modes. So there's one line for every CTD cast. So as you can see, for the lowest mode, there is not much variability in the modal structure for mode 1 up to mode roughly 10. And then for the largest modes, as you can see, the red lines for mode 15, there's starting to be some changes in the vertical structure of the modes, depending on the exact location of where we were doing the profile and the details of n square. Okay, but so we considered in the study that all of the modes had a constant structure in space, and we took the average of the modes. We took the modes from the average n square. So what modes can we observe with the data sets we have in hand? So the horizontal wave number was computed as what's written in the slide here, with Cn the phase speed of internal gravity wave mode n. So that's from resolving the Sturm-Liouville problem, and the vertical wave number was computed through this relation. So the vertical wave number actually depends on depth. And on the left-hand side panel, you're seeing the horizontal wavelengths as a function of the mode number. And on the right-hand side, you're seeing the vertical wavelength as a function of depth and the mode number. And so the largest horizontal wave number is 1 over k max, and it's something like 2 times the ship velocity times the time interval over which were done the binning for making the ADCP data sets, times we added a little bit of smoothing in time to have some to smooth out the currents because the raw data set was a bit spiked at the grid point. So the largest so that's actually the smallest horizontal. The largest horizontal wave number corresponds to a horizontal wavelength of 2.5 kilometers. So that's represented on the slide. Yeah, that's what's called like the Nyquist wavelengths, and the largest vertical wave number was about 48 meters, and that's much smaller. That's much less of a constraint on the observable wavelengths. So overall, the largest observable mode is mode 19, but we also plotted some example for the vertical mode structure, and there's a lot of variability, and adding modes greater than 15, we couldn't see any great improvement into the model reconstruction. Okay, so that's how the section looks like. For the baroclinic current, U on top and V at the bottom. And the color is showing the velocity amplitude in centimeter per second. And the representation of currents is symmetric to the ship's U-turn. So that's the westmost point. So going from east to west, we are crossing the abyssal hill. And then we were going back in the middle of the figure where the distance says it's 0. And you can see actually that there's a nice pattern of a beam that emerges from the hill that can be compared to the theoretical prediction of the internal tight beam. And there's actually a pretty good agreement in terms of slope between what we observe and the theoretical prediction. As you can see, there are also some very intense currents near the bottom. We couldn't find any reason to discard them in terms of flags when we did the quality check. But these currents are a bit suspicious to us because they are reverse and very short time scales, and even the amplitude of the currents is quite large. But yeah, I left them on the plot because we couldn't find any reason to discard them. Anyway, so it looks like an internal tight beam is propagating from the hill, and the clues are manifold. So first, as I said, the beam slope matches the observations, and then the beam velocity polarity is reversed for U, but not V in the inbound versus outbound, which could correspond to the reversing tidal cycle, as you can see on the bottom left schematic here. And in 6 hours time, the U sign changes, but V sign doesn't change. And that's something that we can qualitatively explain with the figure I showed before. So we ask ourselves, can we rationalize and reproduce a similar internal tight beam with simple analytical tools? So we got back to textbooks and tried to interpret the internal wave beam as the superposition of many vertical modes. That's what's illustrated in the plot here. If you take only one mode, this is done for a constant stratification. You have this polarity of whatever variable you want to show that changes on the vertical. If you add 2 modes, 3 modes, 4 modes, then 10 and 25 modes, you are seeing the beam structure that appears with like a pinched structure for the energy. And that is something that is the basis of the work we are doing for reproducing the observations. So the velocity field is written as the sum of the vertical modes, and specifically the analytical field can be written as this. So you have the expressions here for U and V. And so there's a phase shift of pi over 2 of V reference to U. And we're seeking the phase phi n that maximizes the correlation between the observed mode n velocity field and the analytical mode n analytical field. So we are doing this for each mode. And then we want to reconstruct the total field by summing the modes and using the observed modal amplitude. Okay, so I take you through the different stages of the method. So that's what we do for reconstructed mode 1. This is on the top panel, you are seeing observed mode 1 U, and then you have the analytical mode 1 U for a phase that is 0, but then we increase the phase and see if we could get a better agreement between the observed and analytical mode 1. That's the same for V, panel C and panel D, observed and analytical mode 1V. And here on the right hand side, you're seeing the 2-dimensional histogram between observed and analytical fields. And here's the correlation between the fields, and we want we want to maximize the correlation given while changing the phase. So the phase is evolving here. There's a phase step of pi over 32. And as the phase of the analytical wave changes, you can see that the histogram varies. and the correlation varies as well. So for mode 1, we couldn't find that's not a great example because there is no field, there's no phase that corresponds to a good correlation between the observed and analytical waves. So if you're focusing on the right hand side here, you don't see any good agreement between the analytical and observed fields.
Clément, you have 2 minutes.
Oh, okay. So there are modes for which the reconstruction works best, works better at least than compared to mode 1. This is the case for mode 3 here. You can see that at some point the phase allows to have a good agreement between the analytical and observed waves. For mode 5, it's even better. And we were quite surprised actually to observe some wavelengths, some horizontal wavelengths for high modes such as mode 5 here, that really corresponds to the theory. Okay, so then we reconstructed the total field by keeping the modes that had a good correlation between the observed and analytical modes. So the modes that we kept were mode 2, 3, 4, 5, and 6, and we discarded all of the other modes that we were never capable of having a good correlation between analytical and observed structures. And then we had to weight the different solutions, the different modal solutions by energy in each mode. And this is where we struggled a bit to find a good approximation, because the energy in each mode varies a lot, as you can see on the bottom plot here. There's energy in percentage of the total as a function of distance and mode number, and there's quite a lot of variability. But overall, that's our best fit, let's say, between observed and analytical fields. And you can see that we're able to reproduce the structure of the beam pretty well, like at least qualitatively. We have the layered structure that shows up both for U and V, and the correlations are decent. Okay, so we repeated the protocol for the same section at different times, and for some sections the beam shows up very nicely and can be reconstructed accurately. And for some other sections, there were no beam-like structures, so we saw they could be linked to weaker barotropic tidal currents, and there's also some strong scattering of waves by the low-frequency circulation that actually changes quite a lot during the different samplings. We couldn't go any further in the analysis of this. This is to show you an example where it doesn't work really well. The observed velocity structure is very much layered on the horizontal, but it could correspond more to vertical modes instead of internal waves. Okay, so to summarize the result, the simple theory for waves can qualitatively explain the beam structure of the velocity signal. We had to make a lot of approximations for studying this data set, so we only considered some rightward propagating waves. The model content varies a lot through the section, and that's a bit problematic when you want to reconstruct a signal horizontally. It could be because of topographic scattering and energy exchange between the modes, and perhaps scattering by vertical structures. Okay, so yeah, we had to make the assumption that the problem was dominated by the X and Z dimensions, although the wave propagate in 3 dimensions. And the mode 1 was never a good fit in all sections, so that's a bit of a surprise at the beginning, but it could be explained as the mode 1 is, so it's not well represented by a wave structure, but it could be more of a mesoscale vertical mode.